Brilliant is the best way to learn math, data science, and computer science interactively. All their courses have practical applications and are created by award-winning teachers and industry experts. I've been learning on Brilliant for quite some time now, and their interactive questions helped me learn complicated concepts very quickly. I would recommend Brilliant to anyone who wants to learn something new. Right now, Brilliant is offering a 30-day free trial. So go to the website or click on the first link in the description to sign up. When a massive star dies, it does so in a spectacular fashion. Its death throes can briefly outshine an entire galaxy before fading into obscurity. But even in death, this stellar corpse continues to shape the cosmos, scattering the raw materials for planets and life itself. This is the story of a star's death and the staggering implications of its passing. Every star in the night sky is a giant ball of burning plasma. Their light takes millions of years to reach us, leaving us forever separated from the present. Instead, we see a past version of the star. We're only now glimpsing the death throes of stars that died long ago. And those ancient stellar corpses may be the key to understanding our own origins. Stars form in vast clouds of gas and dust, and when they die, they return that material to the cosmos, enriching it with elements forged in the star's core. But how does a star produce these elements? Stars are powered by nuclear fusion in their cores. Hydrogen is converted to helium, releasing tremendous energy and pressure. This pressure supports the star against the relentless pull of gravity. But all stars are not born equal. Those born with a mass at least 8 times larger than our Sun will run out of hydrogen fuel relatively quickly, in a few million years. That's fast in astronomical terms, but slow compared to a human lifespan. When the hydrogen runs out, the star's core begins to collapse under the force of its own gravity. As it collapses, the temperature and pressure at the core increase dramatically. The intense heat and pressure forces helium atoms to slam into each other, fusing them into carbon and releasing even more energy. This causes the outer layers of the star to expand dramatically, turning the star into a red giant. Now here's where things get interesting. 4 stars more massive than 8 times the mass of our Sun. This process of converting helium to carbon and momentarily stabilizing the star happens several more times, each time creating heavier elements until the star's core is mostly iron. Iron is the end of the line. Fusing iron actually requires more energy than fusion releases, so this process actually consumes the star's energy reserves. The core continues to collapse until it is a mere 15 kilometers in diameter. At this point, the star is utterly devoid of energy. Its outer layers, swollen and unstable, explode outward in a supernova, leaving behind a rapidly spinning neutron star. An object with the mass of several suns crammed into a space just 20 kilometers wide. Neutron stars are the most densely packed objects in the universe, so massive that their surfaces are smooth and featureless. When a star more massive than 8 times the mass of our Sun dies, it leaves behind one of these incredibly dense neutron stars. But what happens to the stuff that makes up most of the star? Its outer layers, thrown into space by the supernova explosion, do not simply drift aimlessly. Gravity pulls them together, forming beautiful expanding clouds of gas and dust known as a nebula. These stellar nurseries are the building blocks for new stars and planets. The supernova blast wave generated by the star's explosion sweeps up and disperses these elements over hundreds of light years, fertilizing entire galaxies with the building blocks of life. Even the star's iron-rich core does not go to waste. Supernovas are thought to be the primary source of iron in the universe. Without these stellar explosions, planets like Earth would not have enough iron to form the necessary building blocks of life. So when we gaze up at the night sky, remember that every point of light is a living, breathing entity. Some are red giants, nearing the end of their lives. Others are exploding, scattering the very elements that might one day form new stars and planets. And some may even have already died, leaving behind neutron stars and seeding the galaxy with the building blocks of life. When a massive star collapses, its outer layers are blasted into space in a brilliant explosion. What happens next could make or break planets, shape the chemical makeup of galaxies, and maybe even hold clues to the fate of our universe. In this series, we'll follow the cycle of stellar death and rebirth. First, We will trace the scientific foundations of stellar evolution from the birth of a star to its explosive end. Along the way, we'll explore some of the most iconic remnants, like the Crab Nebula, home to some of the most beautiful and bizarre objects in the cosmos. But even as we marvel at the incredible science behind these stellar furnaces, we will also confront what we don't know. What drives some supernova while others go quietly? How do they compare to the death throes of smaller stars like our Sun? And why do so many of these stellar corpses seem to have planets? We will also see how supernovae touch Earth. Their light fertilizes the planets they leave behind, enriching them with the heavy elements that life needs to flourish. These explosions also created the material and energy that led to the formation of Earth's moon. And by studying them, we have learned to develop new technologies, from nuclear fusion bombs to X-ray lasers. But these stellar remains can also be dangerous. Supernovae are among the most powerful events in the universe. When one occurs, it blasts through the vacuum of space at the speed of light, sending a shockwave that can travel for tens of thousands of light years, stripping away gas and dust and creating bubbles in the interstellar medium. And finally, we will see how supernova may help us answer the greatest question of all. What is the ultimate fate of the universe? By peering into the most distant corners of the cosmos, we can see the universe as it was billions of years ago and use that knowledge to help predict its future. Are we hurtling toward an explosive heat death, or will the expansion of the universe eventually flip and send everything collapsing back together? The answer might lie in the light from these dying stars. The story of supernova is the story of creation through destruction. It is a story that began billions of years ago and continues to this day. Our Sun, like all stars, will eventually die. But when it does, it will explode as a supernova, giving rise to a new kind of star, a white dwarf. These stellar corpses are the building blocks of some of the most extreme environments in the cosmos. Join us as we explore the incredible science that drives these celestial fireworks, the amazing ways that they affect our world, and the burning questions that scientists are working to answer right now. From the tiniest grains of dust to the largest stars in the cosmos, it's all connected. We are made of star stuff, and we are in constant motion. So settle in and get ready for liftoff. In our first episode, we'll meet some of the greatest minds that have pondered the night sky, from ancient astronomers who recorded mysterious guest stars to modern-day space telescopes that captured the explosive edge of the universe. We also see how supernovae have shaped our world and the amazing ways that they continue to influence our lives today. It's the start of an incredible journey through the most violent, beautiful, and mysterious phenomena in the cosmos. So join us and prepare to be amazed. In our universe, governed by the relentless march of physics, every star is destined to die. And the demise of these cosmic giants is both dramatic and inspiring. But before we delve into the violent deaths of stars, we must first understand the serene beauty of their lives. Stars aren't the static twinkling lights in our night sky. They are titanic spheres of plasma, colossal in scale and eternally in motion. Held together by the relentless pull of gravity and fueled by the mind-boggling power of nuclear fusion, these celestial bodies exist in a constant battle between two opposing forces. Gravity relentlessly pulling inward and fusion-powered pressure pushing outward. For most of a star's life, these forces are in balance, creating a stable, radiant star that shines with an otherworldly glow. But like all battles, this equilibrium can be broken. And when it is, the consequences are nothing short of spectacular. Let's start at the beginning. How did these stellar titans come into being? Most stars begin their lives in colossal molecular clouds, vast cold regions of interstellar gas and dust. Within these clouds, gravity plays its orchestrating role, causing the gas to fragment and collapse. As one fragment breaks away from the cloud, it begins to contract under the force of its own gravity. As it does, the particles within it collide more frequently, heating up the core of the protostar that is forming. Eventually, the core becomes so dense and hot that atomic nuclei begin to fuse, forming helium from hydrogen. This moment, when fusion begins, marks the birth of a star. With hydrogen fusion in its core, the star enters the main sequence, the longest and most stable phase of a star's life. Here, The outward pressure from fusion balances the inward pull of gravity. For some stars, particularly those with low mass, this phase can last for trillions of years. Our Sun, for example, has spent 4.6 billion years in this stage and will remain here for another 5 billion. However, not all stars are so fortunate. More massive stars burn through their fuel much faster. A star 10 times the mass of the Sun may exhaust its hydrogen in only a few million years. As hydrogen runs low, the core of the star begins to contract. The increased density and pressure allow heavier elements to fuse. Helium fuses into carbon and oxygen, carbon into neon, neon into magnesium, and oxygen into silicon. Finally, silicon fuses into iron. Each stage occurs faster than the last, until the fusion of silicon into iron lasts only a matter of days. Why does the chain stop at iron? It's because unlike lighter elements, iron does not release energy when fused, it consumes it. Fusion can no longer provide the outward pressure needed to support the star against gravity. And so the star's fate is sealed. With the delicate balance broken, gravity takes over, causing the star to collapse in on itself. Depending on its mass, a star can collapse in different ways. Some, like our Sun, will simply shrink, becoming white dwarfs, incredibly dense remnants of their former selves. Others will explode in spectacular supernovae, leaving behind neutron stars, even denser remnants. And in the case of the most massive stars, the collapse can be so violent that it blasts the outer layers of the star into space in a supernova, leaving behind a black hole, a region of space from which nothing, not even light, can escape. These stellar explosions are not just beautiful cosmic spectacles. They are the engines of creation, forging the heavy elements that are the building blocks of planets and life itself. The iron in your blood, the calcium in your bones, the gold in your crown, all were forged in the heart of a star that exploded in a supernova. So the next time you look up at the night sky, remember that each star has a story to tell, a story of birth and life, of struggle and death, and ultimately of creation. Their light, sometimes dimmed by vast distances, sometimes extinguished by their own gravity, continues to illuminate not just our night sky, but our very existence. This is a supernova remnant. This is what remains after a star explodes. It's called Cassiopeia A, and this is one of the youngest supernova remnants in our galaxy. It's only 340 years old. Here it is again. It's just 11 light years away. That's so close that it's actually visible to the naked eye. If you look up in the night sky and find the constellation of Cassiopeia, look for a small, fuzzy patch near the bright stars of the Big Dipper. That fuzzy patch is the glowing remnant of a star that exploded long ago. Stars like our Sun die slowly. They shed their outer layers into space, leaving behind a dense remnant called a white dwarf. But here, another rule of physics takes over. It's a rule that decides whether a dead star stays dead or comes back to life. It's called the Chandrasekhar limit, discovered in 1930 by the Indian astrophysicist Subramanian Chandrasekhar. He showed that if a white dwarf grows larger than about 1.4 times the mass of the Sun, the pressure of electrons can no longer hold up against gravity. Beyond this limit, collapse is inevitable. In massive stars, collapse comes much sooner. When fusion stops at iron, nothing resists gravity's inward pull. The core collapses in less than a second, crushing protons and electrons into neutrons and releasing an enormous flood of neutrinos. The outer layers rebound off this collapsing core in a titanic explosion, the supernova. Here's the thing about supernova. They're both incredibly destructive and incredibly creative. Supernova blow apart the very stars that create them, scattering the building blocks of new stars across the galaxy. So the material that makes a supernova also makes planets and people, and well, everything. This is how we know we're made of stardust. Every atom of calcium in your bones, every atom of iron in your blood, was forged in the heart of a dying star. We are, quite literally, the children of supernova. When we gaze up at the night sky, we are seeing the ghosts of stars long dead. Those points of light are the tombs of ancestors that lived and died before the birth of our Sun. Even the atoms that make us are far from new. Most of the matter in our bodies was once part of a star that exploded long before the Earth existed. Our bodies are also the explosions of stars. We are the children of the dead. Now let's get back to that moment when a star first ignites. There's something very special going on in that glowing ball of gas. The star is coming alive, undergoing the process that gives it light and heat and life itself. Nuclear fusion. Let me show you how it works. Deep inside a star, temperatures reach 10 million degrees. At such high temperatures, hydrogen atoms smash into each other so hard that they fuse together, forming helium and releasing an incredible surge of energy. This energy pushes outward. As it reaches the surface of the star, it blasts out into space in the form of light and heat. This outward push balances the inward pull of gravity, and the star is born. But this delicate balance doesn't last forever. Stars are born to die. Over billions of years, the star will slowly run out of hydrogen fuel. As the hydrogen supply dwindles, the star struggles to produce enough energy to maintain its light and heat. Without the outward push of nuclear fusion, gravity begins to take over. The star shrinks and heats up, causing the hydrogen that remains to fuse faster. The star shines brighter than ever. This is a red giant. Its outer layers expand until it's hundreds or even thousands of times larger than the sun. As the red giant cools, it ejects its outer layers into space, leaving behind a small, dense remnant. This is a white dwarf. Its size depends on the mass of the original star. If it started out more massive, it will be larger. But no matter the mass, a white dwarf is always extremely dense. If you could squeeze the Earth down to the size of a white dwarf, you would increase its density 1,000,000-fold. If a white dwarf grows too large, it can't shed its outer layers. No force can stop the inevitable collapse. For stars that started out more massive, collapse happens much sooner. When hydrogen runs out, those stars undergo a series of nuclear fusions, creating a heavier element until they produce iron. Fusion stops at iron, because further reactions would require energy rather than releasing it. And this is where the Chandrasekhar limit comes in. When iron builds up in the core of a massive star, fusion stops and gravity takes over. In less than a second, the core collapses, crushing protons and electrons into neutrons and releasing a flood of neutrinos. The outer layers rebound off this collapsing core in a titanic explosion. This is a supernova. Some supernovae occur when a white dwarf in a binary system steals material from its companion star. If it pulls too much material, it can trigger runaway nuclear fusion and cause the white dwarf to explode. Either way, the result is the same, a supernova. These explosions rip apart the very stars that created them. They scatter elements heavier than iron across the galaxy. This is how we know we're made of stardust. Every supernova is a cosmic act of creation. It blows apart the old to make way for the new. It scatters the building blocks of life across the galaxy. So the next time you look up at the night sky, remember this. Those stars up there aren't just twinkling lights. They're furnaces that forge the elements that make life possible. They're the tombs of our ancestors and the cradle of our future. And it all starts with a single, tiny step, a single star coming to life, undergoing the process that gives it light and heat and life itself. Nuclear fusion. The study of supernova has fascinated humanity for centuries. From the first recorded observations of guest stars to the modern era of space telescopes, our understanding of these explosive events has come a long way. Now, while there are hundreds of confirmed supernova in our galaxy, not all of them are created equal. Some stand out due to their peculiar properties, historical significance, or the unique insights they offer into the life and death of stars. Today we're going to talk about 4 such icons of supernova research, each of which has played a pivotal role in shaping our understanding of the cosmos. Let's start our journey with Type Ia supernova, one of the most well-understood and predictable types of supernova. These explosions occur in binary systems where a white dwarf, the dense remnant of a low-mass star, orbits a companion star. Over time, the white dwarf pulls material from its companion, increasing in mass. As it approaches a critical threshold, the white dwarf undergoes a runaway nuclear fusion reaction, resulting in a massive explosion. The beauty of Type Ia supernova lies in their uniformity. Each explosion follows a similar path, providing astronomers with a remarkable standard candle to measure distances within the universe. This consistency stems from the fact that these supernovae occur under nearly identical conditions each time a white dwarf reaches the Chandrasekhar limit, which is approximately 1.4 times the mass of our Sun. the resulting explosion obliterates the white dwarf, leaving behind a rapidly expanding cloud of debris. By comparing the apparent brightness of a Type Ia supernova with its intrinsic luminosity, astronomers can accurately determine the distance to the star system. This capability has been instrumental in our understanding of the universe. In the late 1990s, observations of distant Type Ia supernova revealed that the expansion of the universe was accelerating, a groundbreaking discovery that earned the 2011 Nobel Prize in Physics. Without these remarkable standard candles, our perception of the grand scale of the universe would have been incomplete. Crab Nebula. Our next icon is the Crab Nebula, a celestial tapestry of glowing gas and dust located 6,500 light-years away in the constellation Taurus. In 1054, the Chinese astronomer Su Song recorded a guest star so bright it was visible during the day for over 2 years. This guest star was none other than a supernova that left behind the Crab Nebula. Supernova 1054 was witnessed by various cultures across the globe, including Arab, Japanese, and Native American astronomers. It marked the first supernova to be observed during modern times. The Crab Nebula is home to a pulsar, a rapidly spinning neutron star that emits beams of radiation. This pulsar, known as the Crab pulsar, rotates 30 times a second and is believed to be the heart of the exploded star. The nebula is a rich ground for scientific exploration, offering insights into the behavior of shock waves and magnetic fields. Telescopes have revealed a plethora of fascinating features, including knots and filaments expanding outward from the pulsar. One of the most striking aspects of the Crab Nebula is its continuous evolution, captured in stunning detail by the Hubble Space Telescope over the past 3 decades. As the nebula expands, it creates a bubble of hot gas and dust, driving a shock wave into the surrounding medium. This interaction generates intricate structures that serve as cosmic laboratories for studying high-energy processes.
Ouch!
The Crab Nebula stands as a testament to the power of human observation and the scientific advancements that have allowed us to witness the birth of a supernova remnant. Its enduring presence in the sky serves as a constant reminder of the dynamic nature of our universe. Pulsars. Pulsars are among the most intriguing objects in the universe. They're neutron stars, remnants of massive stars that have exploded as supernova. These highly dense objects rotate rapidly and emit beams of radiation that sweep across space like a cosmic lighthouse. Discovered in 1967 by radio astronomer Jocelyn Bell Bernal, pulsars quickly became a subject of intense study. The first pulsar found was named CP1919, now known as PSR B1919+21. Its regular pulses, arriving with clock-like precision, revolutionized our understanding of stellar remnants. Since then, thousands of pulsars have been identified, each with its unique characteristics. Pulsars are not just fascinating astronomical phenomena, but also invaluable tools for scientific exploration. Their precise timing and strong signals enable astronomers to probe a wide range of phenomena, including tests of general relativity, the search for gravitational waves, and the study of interstellar matter. Moreover, pulsars play a crucial role in understanding supernova remnants and the life cycle of stars. By analyzing their properties, astronomers can gain insights into the conditions that prevailed at the end of a massive star's life. For example, pulsars can reveal details about the star's core collapse and the formation of the neutron star itself. The discovery of pulsars opened up new frontiers in astronomy and astrophysics. They continue to be an active area of research, promising further revelations about the extreme conditions that exist in our universe. Magnetars. Magnetars are a rare class of neutron stars characterized by their exceptionally powerful magnetic fields. These enigmatic objects are born from the explosive deaths of massive stars and possess magnetic fields millions of times stronger than those of ordinary neutron stars. The exact mechanism behind their formation is still not fully understood, but it is believed that they're intense. Magnetic fields arise from the rapid rotation of the neutron star and the conservation of angular momentum during the star's collapse. Magnetars exhibit a range of unusual properties and behaviors. Their magnetic fields are so strong that they can penetrate the neutron star's crust and alter its structure. This leads to a variety of observable phenomena, such as starquakes, glitches, and outbursts of X-rays and gamma rays. Starquakes are sudden shifts in the neutron star's magnetic field, caused by the sudden release of magnetic energy stored in the crust. Glitches, on the other hand, are abrupt changes in the pulsar's rotational speed and are thought to occur when the neutron star's crust slips past its core. The outbursts of X-rays and gamma rays from magnetars are thought to be triggered by the twisting and fracturing of their magnetic field lines. These emissions play a significant role in the dynamics of supernova remnants and the surrounding interstellar medium. Studying magnetars provides astronomers with a unique opportunity to explore the behavior of matter under extreme conditions of density and magnetic field strength. By unraveling the secrets of these enigmatic objects, researchers hope to shed light on the fundamental properties of neutron stars and the nature of strong magnetic fields in the universe. The legacy of these icons, the 4 icons of supernova research, represent just a fraction of the explosive events that shape our universe. From the predictable brilliance of Type Ia supernova to the captivating beauty of the Crab Nebula, from the enigmatic nature of pulsars to the extreme power of magnetars, each of these phenomena offers a unique window into the life and death of stars. Supernova are not just destructive events. They are the engines of creation, driving the recycling of matter in galaxies and seeding the cosmos with heavy elements. Understanding these stellar explosions is crucial for comprehending the chemical evolution of the universe and the origins of planetary systems. While we have made significant strides in unraveling the mysteries of supernova, much remains unknown. Gamma-ray bursts, hypernovae, and the potential for stars to produce more supernova are areas that continue to captivate astronomers. The study of supernova has come a long way from the telescopic observations of the 17th century to the sophisticated space missions of today. With each new discovery, we deepen our appreciation for the grandeur and complexity of the cosmos. The legacy of these icons will continue to inspire generations of scientists to push the boundaries of our knowledge and explore the explosive wonders of the universe. As technology advances, we can look forward to even more detailed and precise studies of supernova, revealing their full magnificence and importance in the grand tapestry of the cosmos. So there you have it, a brief overview of 4 icons of supernova research that have shaped our understanding of stellar explosions. The universe is vast and filled with wonders that continue to amaze us. One such wonder is the supernova, a stellar explosion so bright it can outshine an entire galaxy. But did you know that there are some supernova that are so incredibly powerful that they defy even this explosive description? Enter the hypernova, an event that takes the power of a typical supernova to a whole new level. In today's episode, we will explore the incredible power of the hypernova and what it means for the life cycle of stars. First, let's take a closer look at the supernova itself. A supernova occurs when a star runs out of fuel and collapses under its own gravity. This collapse can be so powerful that it causes the star to explode, releasing a tremendous amount of energy into space. Supernova are responsible for creating many of the elements that are essential for life, such as iron, gold, and uranium. They also play a key role in the life cycle of stars, helping to recycle the material from old stars into new ones. But while supernova are impressive, the term hypernova refers to an even more extreme version of these stellar explosions. A hypernova is an extraordinarily powerful supernova that releases up to 10 times more energy than a regular supernova. These events are relatively rare, but they are thought to occur when a star that is more than 30 times the mass of the Sun collapses into a black hole. As the star collapses, it releases an enormous amount of energy in the form of a jet that blasts through the star's outer layers. This jet can extend for thousands of light years and is powered by the intense energy released during the collapse. One of the most intriguing aspects of hypernovae is their possible connection to gamma-ray bursts, some of the brightest and most violent explosions in the universe. Gamma-ray bursts are brief but intense flashes of gamma rays that can outshine galaxies by a factor of 10 billion. These bursts can be seen at incredibly high redshifts, indicating that they occurred in the early days of the universe, while the exact mechanism that produces gamma bursts is still debated. It is thought that a fraction of them are associated with hypernovae. Specifically, when a jet from a hypernova is pointed in our direction, it can produce an intense flash of gamma rays that we observe as a gamma ray burst. It's important to note that not all gamma ray bursts are created equal. Astronomers divide them into two main categories based on their duration. Long-duration bursts typically last for more than 2 seconds and are thought to be associated with the collapse of massive stars into black holes, i.e., hypernovae. On the other hand, short-duration bursts last for less than 2 seconds and are believed to result from the merger of two neutron stars or a neutron star and a black hole. These short bursts are thought to be less common than long-duration bursts, but they are also much more energetic. Hypernovae are truly remarkable astronomical phenomena that remind us of the incredible power and diversity of the universe. While we have come a long way in understanding these events, there is still much to learn. As we continue to explore the cosmos, we may discover even more secrets of the hypernova and its role in the life cycle of stars. So what do you think? Does the idea of a star exploding with such force as a hypernova both terrify and fascinate you? Or do you find the possibility of new stars being born from this explosion a source of hope and wonder? Share your thoughts in the comments below. And don't forget to subscribe for more exciting videos about the universe and beyond. Every big thing that ends also begins anew. Like when a star dies, it blasts away its outer layers in a spectacular explosion called a supernova. These blasts are so powerful that they can plow through huge clouds of interstellar gas and dust. When the dust settles, new stars can form out of the debris. So in a sense, every generation of stars plants the seeds for the next. We're actually pretty lucky that this happens, because without these stellar nurseries, there wouldn't be many stars or planets around to get in the way of those pesky gamma-ray bursts. But it turns out that supernova might not just be agents of creation, they might also be agents of destruction. They might trigger the formation of new stars, but only after they destroy the old ones. In 2012, astronomers studied a region of space called the Crab Nebula and found evidence of this stellar destruction and creation cycle in action. The nebula is 1344 light-years away and contains several clusters of hot young stars. And based on computer models, researchers think that a supernova explosion that occurred about 1 million years ago may have triggered the collapse of the very clouds that now shine with newborn stars. The shockwave from the explosion seems to have compressed the gas in the nebula just enough to kickstart star formation. And since then, the stellar winds from the newly formed stars have blown the gas back out into a bubble. What's more, this cycle might even extend to planetary systems. When a supernova occurs, it scatters heavy elements like iron, silicon, and oxygen into the surrounding interstellar medium. These elements are vital for life as we know it. And without the enrichment from ancient stellar deaths, Earth itself could never have existed. In fact, you could say that you are literally made of star stuff. But for all our progress, big questions remain. For example, why do some stars like Betelgeuse die quietly, collapsing into black holes with little outward sign, while others like Rigel explode violently as supernova? What determines whether a supernova will leave behind a neutron star, a magnetar, or a black hole? And how exactly do supernova shock waves influence the balance between destruction and star formation across galaxies? Answering these questions sit at the frontier of astrophysics. It will take more powerful telescopes and perhaps even new theories of how matter and energy behave under the most extreme conditions in the universe. For now, though, we can appreciate the irony. Gamma-ray bursts and supernova are among the most violent phenomena in the cosmos. Yet they are also the cosmic balance, the death and rebirth of stars that make galaxies like the Milky Way. Planets like Earth, and maybe even life as we know it possible. Researchers say that the results of this study have implications for understanding star formation, not just in the Milky Way, but in other galaxies as well. If these cycles of stellar death and rebirth are common throughout the cosmos, then it may be that supernova play a key role in the evolution of galaxies. In other words, the death of one generation of stars may be the key to the birth of the next. Now you need to watch worst-case scenarios, supernova, or check out How Do We Know the Universe is Expanding? In October 1993, an amateur astronomer named Robert McNaught peered into the night sky above Australia. Wasn't looking at any particular target. Instead, he was doing what backyard astronomers do, scanning the horizon with the hope of discovering something interesting. What he saw that night was neither expected nor common, a bright point of light in the constellation Sagittarius. With the help of some colleagues, McNaught confirmed his suspicions. This was no ordinary star. It had suddenly brightened by several thousand times, making it visible to the naked eye from anywhere on Earth. McNaught had witnessed a supernova, the explosive death of a star. For most people, this would have been the end of the story, but for astronomers, it was just the beginning. To understand why, let's rewind to the beginning of the story, the birth of the supernova. At the heart of every supernova lies a massive star, many times larger than our Sun. Eventually, these stars run out of hydrogen fuel, causing their cores to collapse under the force of their own gravity. In mere seconds, these cores can collapse from millions of kilometers to just a few dozen, triggering a huge explosion. The outer envelope of the star is blown away into space. And if the star was massive enough, the core collapses to form either a neutron star or a black hole. The ejected material, along with the shock wave of the explosion, creates a cloud of gas and dust called a supernova remnant. Over millions of years, this material will disperse into the galaxy. If the star was in a solar system like ours, its supernova would seed the disk of dust and gas that eventually coalesces into the building blocks of planets, asteroids, and comets. The chemical building blocks of life. Supernova played a similar role in seeding the galaxy.
Oh.
We wouldn't be here without them. But while supernova create new things, they can also destroy. Gamma rays and cosmic rays from a nearby supernova could strip away parts of Earth's ozone layer, exposing life to dangerous levels of ultraviolet radiation. This, in turn, could trigger mass extinctions. Some scientists even speculate that past extinction events in Earth's history may have been linked to cosmic catastrophes. Today, we know that no stars massive enough to explode are found within the 30 light-year radius where such an event would be hazardous. The closest candidate, Betelgeuse in the constellation Orion, lies about 650 light-years from Earth. So while a supernova in our cosmic neighborhood would be a spectacular sight, it would pose no serious threat to our planet. Still, the sheer energy released by these explosions is staggering. A supernova can outshine an entire galaxy, releasing the equivalent of 100 trillion nuclear bombs. Their light can be seen from billions of light-years away. Thanks to this brightness, supernovae have served as astronomical lighthouses for centuries, helping astronomers map the structure of our universe. It's easy to see why. While the average galaxy contains only a handful of stars that go supernova each century, each supernova is bright enough to outshine its host galaxy, making it the brightest object in the night sky for months. That makes them ideal standard candles for measuring cosmic distances. By comparing the observed brightness of a supernova with its absolute brightness, astronomers can easily calculate its distance. And because this relationship is well understood, supernova can reveal much more. By studying how a supernova's brightness changes over time, astronomers can learn how far away it lies. And by comparing this distance with the rate at which the light is fading, they can calculate how fast the universe is expanding. This has allowed cosmologists to confirm that the expansion of the universe is accelerating. Another thing that supernova can tell us is how massive the star was at the beginning of the explosion. By analyzing the spectrum of the light, astronomers can measure the velocity of different elements flying away from the star during the explosion. Because these elements move at different speeds, their velocities can be used to infer the star's pre-supernova mass. In other words, the heavier the star, the faster its outer layers recede during the explosion. This analysis reveals the star's mass at the moment it went supernova. And so by observing a single supernova, astronomers can gain insights into a wide range of topics. From the expansion rate of the universe to the properties of the star that exploded. So let's get back to the discovery of SN 1993J, the supernova that Robert McNaught identified that crisp October night. In the years since its discovery, SN 1993J has become a goldmine for astronomers. Its distance has been measured in different ways, allowing researchers to calibrate their distance measurements. Its spectrum has been studied extensively to learn more about the composition of the star that exploded. And its light has been analyzed to measure how fast the universe is expanding. SN 1993J also represents a turning point in the history of astronomy. For the first time, astronomers have witnessed the death throes of a star in real time. Telescopes around the world turned to the Tarantula Nebula, home of SN 1993J, providing a continuous stream of data. Astronomers were able to capture every phase of the supernova, from its initial outburst to the emergence of a glowing shell of material ejected during the explosion. Thanks to these observations, astronomers now know more about supernova than ever before. One key question, however, remains unanswered. How do these stars produce the heavy elements in the first place? The leading theory hinges on a process called rapid neutron capture, or the R process for short. Here's how it works. During a supernova, protons and neutrons combine to form elements heavier than iron, however. These elements are unstable and decay quickly. The R process occurs when a neutron-rich nucleus captures additional neutrons before it has a chance to decay, allowing it to reach stability. But until the detailed observations of SN 1993J, astronomers couldn't determine which elements were produced in such a way. Now, by analyzing the light from this supernova, scientists have discovered the missing link, a series of elements that show clear evidence of being forged in the R process. Together, these observations have revealed the inner workings of one of nature's most violent phenomena. So why do supernovae matter? Well, for starters, they're simply uninspiring. The sudden appearance of a bright star in the night sky has captured humanity's attention for thousands of years. Supernovae have been recorded in Chinese, Japanese, and Arabic texts dating back thousands of years, and who could blame them? In a single night, a dim speck of starlight can brighten by thousands of times, becoming visible to anyone on Earth. In fact, the brightest supernova ever recorded in the Northern Hemisphere occurred in 1054. And was so bright that it remained visible for 23 months. According to an account by the Chinese astronomer Shen Kuo, it shone 10 times brighter than Venus and could even be seen during the day. The remnant of this supernova, known as Cassiopeia A, is still visible today. And while it is too faint to be seen with the naked eye, it can be spotted with a small telescope. But supernovae are more than just beautiful astronomical events. They are fundamental to our understanding of the universe. By studying supernovae, we can learn more about the chemical activity that gives rise to life on Earth. We can also use them to measure the rate at which the universe is expanding, a key measurement for cosmology. In addition, by searching for supernovae in distant galaxies, we can detect the presence of dark energy, a mysterious force that appears to be speeding up the expansion of the universe. Dark energy remains one of the biggest mysteries in modern physics, and supernovae are one of our best tools for unraveling its secrets. SN 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, was the first supernova to be detected in our galactic neighborhood in more than 300 years. It was also the first to be studied in detail with modern telescopes. No, SN 1987A provided an unprecedented opportunity to observe a supernova up close. For the first time, astronomers were able to study the explosion in real time as it unfolded over weeks and months. The wealth of data collected during this event revolutionized our understanding of supernovae. It showed that these explosions are incredibly diverse, ranging from slow and steady events to fast and furious outbursts. The observations also revealed the complexity of the material ejected during the explosion, showing that it is not simply a homogeneous cloud of gas and dust. Instead, it is a highly structured and dynamic environment, with shocks, bubbles, and knots of material moving at different speeds. In the aftermath of SN 1987A, the ejected material has formed a beautiful hourglass-shaped nebula that continues to evolve today. This nebula is rich in heavy elements such as iron, nickel, and zinc, which were produced in the heart of the exploding star. These elements will eventually be dispersed into the interstellar medium, where they will form new stars and planets. In this way, supernovae play an essential role in the recycling of matter in the universe, ensuring that the building blocks of life are constantly being renewed. As we peer deeper into space, we are witnessing not only the birth and death of stars, but the creation of the very elements that make life possible. Supernovae are a reminder that our place in the universe is both privileged and precarious. We exist thanks to the explosions that scattered the building blocks of life across the cosmos. But we must remain vigilant, for the same forces that created our world can just as easily destroy it. The study of supernovae is a testament to the power of human curiosity and the relentless march of scientific progress. From the first amateur astronomers who recorded the appearance of bright stars in the night sky to the modern-day observers who capture images of distant nebulas, We have come a long way in our quest to understand the universe. Each new discovery brings us closer to unraveling the mysteries of the cosmos and reveals the intricate beauty of the natural world. So let us continue to explore, to discover, and to marvel at the wonders of the universe. For in doing so, we are truly living up to our nature as human beings. For people living on Earth, the sky is full of familiar sights. Stars twinkle, and planets wander among them. But the universe never ceases to amaze. Every few centuries, our home galaxy gives us a show. It's a light show like no other. A star explodes, scattering its guts across the cosmos and leaving behind a glowing cloud of gas and dust. We call these stellar explosions supernova. And while they are rare, they are so bright that when they happen, they dominate the night sky. Even worse, or maybe even better, they can be seen in broad daylight. Supernova are rare on human timescales. In a galaxy like the Milky Way, astronomers expect only 1 or 2 per century to be visible. When they occur, they can be so bright that they dominate the night sky and even appear in broad daylight. For ancient peoples who lived under unpolluted skies, such events were unmistakable. Long before telescopes or astrophysics, humanity was already keeping watch over stellar death. This segment tells the story of how human eyes, then human instruments traced the violent ends of stars from ancient Chinese astronomers to Tycho Brahe and Johannes Kepler, to the observatories and space telescopes of today. Ancient records the sky remembers. The earliest surviving records of supernova come from Chinese astronomers, who meticulously tracked guest stars that appeared suddenly and lingered in the heavens before fading away. In 185 CE, Chinese records describe a star that shone in the southern sky for months. Almost certainly a supernovae, the first ever recorded in human history. In 1006 CE, one of the brightest supernovae in recorded history appeared. Observers from China, Japan, the Middle East, and Europe wrote of a star so bright it cast shadows at night and was visible during the day. Modern astronomers now know its remnant as a vast expanding shell of gas in the constellation Lupus. In 1054 CE, Chinese and Japanese astronomers recorded the explosion that created the Crab Nebula. Native American petroglyphs may also preserve memories of this event, showing a brilliant star near the crescent moon. To these early cultures, supernovae were not astrophysics. They were omens, wonders, or divine messages. But their careful records, passed down through centuries, remain invaluable to modern scientists trying to piece together the cosmic past. The scientific revolution astronomers in the Middle Ages were often employed by kings or the church, and their work was considered more a branch of theology than science. That began to change in the 16th century, when some thinkers started to question long-held assumptions about the nature of the universe. One of those was the idea that the heavens were perfect and unchanging. Enter Tycho Brahe, a Danish nobleman who made detailed observations of the solar system and published the first accurate star maps. In 1572, he noticed a new star in the sky. At first it was about as bright as the North Star, but within a few weeks it was so bright it rivaled Venus. It remained visible for 2 years before fading from view. Tycho recorded its brightness and position with unprecedented precision, concluding that the star was much farther away than any comet or planet. This discovery struck a blow against the Aristotelian idea of an unchanging, perfect heaven. Tycho's De Stella Nova argued that the heavens themselves could change, that stars were not eternal. The death of a star seen with the naked eye had shaken the foundations of cosmology. Tycho, however, did not live to see how his observations would change the world. He died believing the star simply moved into and out of the solar system. That idea was taken up by the Polish astronomer Johannes Kepler, who used Tycho's meticulous data and his own understanding of optics to make sense of what was really happening. Kepler concluded that the star had exploded, throwing off its outer layers and leaving behind a glowing cloud of gas. In 1610, he predicted that the star would reappear in the same place, shining just as brightly as before. And in 1630, he was proven correct when the star reappeared exactly as predicted, shining brilliantly in the constellation Ophiuchus. It was the first time in history that a scientific prediction had been made and confirmed. Supernova today, with the advent of modern telescopes, we are able to see supernova in greater detail than ever before. In 1987, an amazing opportunity came along. A supernova exploded in the Large Magellanic Cloud, a small satellite galaxy of our own. This was the closest supernova to Earth in modern history. It gave astronomers a chance to study these objects up close. The light from this explosion reached Earth in 1988, and it remains one of the brightest events ever witnessed. Supernovae are divided into two categories based on how they fade over time. Type 1 supernovae have light curves that can be fairly well approximated by a single power law. They all look alike, and they serve as standard candles, allowing astronomers to measure distances to other galaxies. Type 2 supernovae, on the other hand, do not fit this description. Their light curves decline more slowly and have complex shapes. They are thought to be caused by the collapse of massive stars. In either case, supernovae play a vital role in the universe, seeding space with heavy elements, enriching gas clouds, and enabling the formation of planets and life itself. Today, astronomers are working on a number of exciting projects to learn more about supernovae. The James Webb Space Telescope will allow us to peer deep into space and discover the details of distant exploding stars. By studying these stellar explosions, we are not only unlocking the secrets of the universe, but also learning more about ourselves and the forces that shaped life on Earth. So next time you look up at the night sky, remember that those twinkling lights are not just pretty to look at. They are windows into the past and clues to the future. A new star. How often have you heard that phrase in your lifetime? If you're anything like me, probably quite often. But when was the last time you actually saw a new star appear in the night sky? And no, I don't mean one of those low-budget sci-fi flicks premiering on a streaming service. I'm talking about an actual astronomical event, a true new star born from the death throes of a giant. The last time this happened was more than 300 years ago. It was 1604, and German astronomer Johannes Kepler was busy formulating his laws of planetary motion. Then he noticed something strange, a bright star in the constellation Ophiuchus, the serpent bearer, shining brighter than any other star in the firmament. Now we know it was a supernova, the spectacular death explosion of a massive star. Like others before him, Kepler recorded its brightness, its color, and its place among the constellations. Not unlike his predecessors, he linked this violent change in the heavens to his new astronomical laws, which described the orderly elliptical paths of planets around the sun. For Kepler, these supernovae represented not only cosmic events but also turning points in the history of science. They showed that the heavens were not static, that they changed and evolved according to mathematical laws. And yet neither Kepler nor any other astronomer at the time knew that they were witnessing the last supernova visible to the naked eye. It's the last one until now. Welcome to the channel. This is the last naked eye blast, the last supernova visible without a telescope, the end of an era. What followed was nearly 4 centuries of scientific darkness, a time when astronomers had no idea how many supernovae were happening out there. They couldn't observe the birth of new stars, because their eyes were blinded by dust clouds and the limitations of telescopes. But then, in the 20th century, the floodgates opened. In 1931, astronomer Walter Baade classified supernovae into different types, beginning the taxonomy that scientists still use today. Type 1, stars that explode after exhausting their hydrogen supply. Type 2, stars that show hydrogen in their spectra. And Type La supernova, that can be used as standard candles to measure distances in space. Then came the observations that made supernova into a physical science. In 1953, the discovery that they scatter heavy materials like iron and nickel into space, along with the confirmation that these explosions occur in distant galaxies, not in our own. In the late 20th century, technological leaps pushed the frontier even further. Space telescopes like Hubble, X-ray observatories like Chandra, and radio telescopes around the world gave us multi-wavelength views of supernova remnants. We learned to trace shock waves, measure neutron stars, and modeled the physics of explosions in ways earlier observers could never have imagined. One of the most important modern milestones was SN 1987A, supernova in the Large Magellanic Cloud, a neighboring galaxy. Visible to the naked eye in the southern hemisphere, it became the closest supernova observed in nearly 4 centuries. For the first time, astronomers detected not just light streaming from the core collapse, but also neutrinos, tiny ghost particles that rarely interact with matter. These observations directly confirm decades of theoretical work on how supernovae explode. Today's cosmic watch, now astronomers no longer wait passively for rare naked-eye events. Automated sky surveys, robotic telescopes, and space observatories constantly scan the heavens, catching supernovae in galaxies millions or even billions of light-years away. Each year, modern astronomy finds thousands of supernovae, each one a new data set, each one teaching us more about stellar death and the life that follows. And yet, despite all our technology, the sense of wonder remains. To imagine Tycho gazing upward in 1572, or a Chinese astronomer recording the Crab star in 1054 is to share in a timeless human experience, watching the cosmos change before our very eyes. From records to revelations, the human gaze, whether naked eye, early telescope, or modern observatory, has carried us from superstition to science. Where once a new star meant an omen, now it means the death of a sun, the forging of elements, the shaping of galaxies. Humanity has gone from recording strange appearances to understanding that they are the universe's way of renewing itself. All that remains is for us to watch, learn, and wait for the next time the heavens blaze anew. So if you ever hear that there's a new star in the sky, don't dismiss it as hype. It could be the universe's way of telling us something profound. It could be the death of a sun, the birth of a new world. It could be a message from the stars. Explosions, stellar death throes, supernova are among the most dramatic events in the universe. But the story of supernova is not finished. Even now, stars in our galaxy are preparing for their final act, and astronomers are watching closely. These coming explosions will not only dazzle our skies, but also deepen our understanding of the cosmos itself. From the fiery fate of Betelgeuse to the way supernova allow us to measure the universe's expansion, the future of stellar death is intertwined with our own search for cosmic destiny. Few stars capture public imagination, like Betelgeuse, the red supergiant in Orion's shoulder. Visible to the naked eye, Betelgeuse is enormous, about 700 times the diameter of the Sun and nearing the end of its life. In astronomical terms, its time is short. At some point within the next 100,000 years, a Betelgeuse will explode as a core-collapse supernova. When it does, it may shine as bright as a crescent moon, visible in daylight for weeks. In 2019, Betelgeuse dimmed dramatically, sparking speculation that the explosion might be imminent. While the dimming was later explained by dust and surface activity, the event was a reminder that this star is fragile, unstable, and waiting for its final collapse. For humanity, Betelgeuse's death will be spectacular but safe. At 650 light-years away, it poses no danger. Instead, it will offer scientists a once-in-a-lifetime laboratory to test supernova theories in real time with the best instruments ever built. But individual stars are only part of the story. Even more important are the clues supernova give about the nature of space and time. During the Cold War, scientists learned to use stellar explosions as standard candles to measure distances to faraway galaxies. Here's how it works. Imagine placing two candles 10 feet apart and noting that one appears twice as far away as the other. If you know the exact brightness of each candle, you can calculate exactly how far away they are. Scientists do the same thing with supernova. They find a supernova of known brightness and compare it to similar explosions that appear brighter or dimmer. From this, they can work out how far away the supernova really is. And with this distance in hand, they can calculate how fast the universe is expanding. This discovery in the 1990s by two independent teams of scientists using supernova to measure the universe was a scientific sensation and had a Nobel Prize. It revealed that the expansion of the universe is speeding up. It's driven by something mysterious known as dark energy. Without supernova, we might never have detected this phenomenon and would still be blind to one of the most profound mysteries in science. Dark energy has led to a new understanding of the universe and also a new set of questions. Does dark energy continue to push the universe apart at a steady rate, or does it grow stronger with time? If it strengthens, will expansion eventually rip apart not just galaxies, but also solar systems and molecules, and eventually living things themselves? Or will gravity someday overcome expansion, pulling the universe into a big crunch? Supernova give us the tools to confront these ultimate questions. By continuing to measure the speed of cosmic expansion, supernovae also tell us about stellar life cycles. Some stars explode 1 or 2 times before settling down as white dwarfs. A rare few explode up to 3 times, shedding their outer layers each time and growing an elaborate set of accretions around their cores. Astronomers think these bizarre objects could be the key to understanding the heaviest elements in the universe, including gold and uranium. One day, scientists hope to catch a star exploding more than once and unravel the mystery of these stellar corpses. Supernovae are also giving us a complete 3-dimensional map of our galaxy, one that will help us understand where new stars will form in the future. That's because after a supernova explosion, a bubble of gas is left behind. Over time, this bubble expands, pushing against the surrounding dust and revealing the distribution of matter in our galaxy. Supernovae are thus not just the death throes of stars, but also the cradle of new stellar life. Explosions may also explain why life arose on Earth. As we have seen, supernovae scatter heavy elements throughout the galaxy, including the iron, nickel, and zinc that are vital for life as we know it. Astronomers believe a supernova explosion occurred near our solar system about 650 million years ago, leaving behind a cloud of such elements. This second genesis might have kicked off the first life forms on our planet. Supernovae thus bring us full circle. From the birth of our solar system to the death throes that may have created life on Earth, to the explosions that may end it. All of this is to say that the story of supernova is not over. In fact, it is just beginning. Every explosion brings new discoveries and raises new questions about our place in the cosmos. Each supernova is a reminder that our existence is fragile and fleeting, but also that our curiosity and spirit of exploration will never die. This is the first episode of our mini-series on stellar death. For millennia, humans have looked up at the night sky and marveled at its beauty and its mystery. Among the most captivating sights are the stars, which have held both fascination and terror for our species since we first looked up at them. In particular, there's one kind of star that's captured our imaginations like no others. The exploding stars, the supernova, they're beautiful, inspiring, and deadly. They can outshine galaxies and be seen from thousands of light years away. But what are they, and how do they work? In today's video, we are going to explore the science behind supernova and find out why they are so important to our existence. Let's start by asking what a supernova actually is. A supernova is the name given to the explosive death of a star, but not all stars explode in the same way. There are 2 main types of supernova, Type 1 and Type 2. Type 1 supernova occur in binary systems where a white dwarf star, which is the dense remnant of a sun-like star that has exhausted its nuclear fuel, pulls material from its companion star. Over time, the white dwarf's mass increases until it reaches a critical point and suddenly collapses, triggering a runaway nuclear reaction that blasts the star's outer layers into space. Type 2 supernova, on the other hand, occur in massive stars 8 times the size of our Sun or larger. As these stars begin to run out of fuel, their cores contract and heat up, causing an outward explosion that blasts the star's outer layers into space. Both types of supernova release tremendous amounts of energy, light and heat, which can be observed from Earth as a bright, beautiful explosion. But the true wonder of supernova is what happens after the initial explosion. The material ejected from the star forms a cloud of gas and dust that remains visible for centuries as a nebula. These nebulae are the birthplaces of new stars and planets, and the elements forged in the dying star's core, such as iron, oxygen, and calcium, are dispersed into the galaxy, seeding the formation of new life. In fact, all the elements heavier than hydrogen and helium were created in the cores of exploded stars. So without supernova, the universe as we know it could not exist. Not only would there be no planets or life, but no Earth or Sun either. The study of supernova is a relatively new field in astronomy, dating back only to the 19th century, when modern telescopes became powerful enough to detect them. Since then, we've learned a lot about these fascinating objects and their role in the universe. But there's still much we don't know. Supernova are incredibly rare events, and trying to observe one can be like trying to watch a car crash in slow motion. You know it's going to happen eventually, but you have no idea when and where. However, with the advent of new technologies such as the James Webb Space Telescope, the Vera C. Rubin Observatory. In upcoming gravitational wave detectors, we are poised to enter a new era in supernova research. We may soon be able to observe the collapse of a star's core in real time, not only in light, but in neutrinos and gravitational waves, essentially watching the very heartbeat of a star as it dies. We may finally solve the puzzles of gamma-ray bursts and magnetars, or discover entirely new phenomena that defy our current theories. But beyond the science, there's also something deeply personal in the story of supernova. They're the reason we exist. Without them, Earth would be a barren rock, stripped of the elements needed for life. Every atom of iron in our blood, every atom of oxygen we breathe, every atom of calcium in our bones came from the death of a star. When we look up at Orion and imagine Betelgeuse's future explosion, we are not just watching a star's destiny. We are glimpsing our own origins and perhaps our own fate. Supernova are cosmic paradoxes, death that gives life, explosions that seed creation, destruction that lights the way to understanding. From ancient skywatchers recording mysterious guest stars to modern astronomers probing the farthest reaches of the cosmos, humanity's gaze has always been drawn to these fiery deaths. The cycle of stars is the cycle of the universe itself. Stars are born, they live, they die, and from their ashes, new stars rise. And within this endless cycle lies the story of us, creatures of stardust, watching the universe learn about itself through the deaths of its suns. When stars die, they give us life. That is the ultimate lesson of the supernova, a lesson written not only in the sky, but in every atom of our being. If you liked the video, don't forget to subscribe and hit the bell icon to never miss an upload. And if you really want to help us grow, you can consider becoming a patron where you get access to exclusive content and be able to give your input on each video. Thank you very much for watching. I'll see you next time.